The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
And up on the web now are lots of sections, including this conjugate gradient. So today is the end of the conjugate gradient discussion. And it's kind of a difficult algorithm. It's beautiful and slightly tricky. But if I just see what the point is of conjugate gradients, we don't have to check that the exact formulas that I listed here. So that's one step of conjugate gradients, going from k minus 1 to k. And we'll look at each of the 5 steps in the cycle, but without patiently checking all those formulas. We'll just sort of see how much work is involved. But let me begin where we were last time, which was Arnoldi. So Arnoldi was a Gram-Schmidt-like algorithm, not exactly Gram-Schmidt, that produced an orthogonal basis. And that basis is the basis for the Krylov subspace. So that each new vector in the each new basis vector in the Krylov subspace is found by multiplying by another power of a. But that's a terrible basis. So that the basis that we get from these guys has to be improved, orthogonalized, and that's what Arnoldi does. And if we look to see what it does matrix-wise, it turns out to be exactly, have that nice equation that we're creating a matrix Q with the orthogonal vectors and a matrix H that tells us how they were connected to the column, to the matrix A. Okay, so that's that's the central equation, and the properties of H are important. So we saw that, so the key property was, in general, we've got it's full up in that upper corner, just the way Gram-Schmidt would be. But in case A is a symmetric matrix, then we can check that H will be symmetric from this formula. And the fact that it's symmetric means that those are zeros up there, because we know there are zeros down here. We know there's only one diagonal below the main diagonal. And if it's symmetric, then there's only one diagonal above. And that's the great case, that the symmetric case, I'm going to take 2 seconds just to say, here's the best way to find eigenvalues. We haven't spoken one word about computing eigenvalues, but this is the moment to say that word. If I have a symmetric matrix, eigenvalues are way, way easier for symmetric matrices. Linear systems are also easier, but eigenvalues are order of magnitude easier for symmetric matrices. And here's a really good way to find the eigenvalues of large matrices. I assume that you don't want all the eigenvalues. I mean, that is very unusual to need many, many eigenvalues of a big matrix. You're probably those high eigenvalues are not really physically close, good representations of the actual eigenvalues of the continuous problem. So we have continuous and discrete that are close for the low eigenvalues, because that's right. That's where the error is smooth. High eigenvalues are not so reliable. So for the low eigenvalues, here's a good way to do them. Do Arnoldi, and it gets named also now after Lanczos, because he had this eigenvalue idea, run that for a while. Say if you want 10 eigenvalues, maybe go up to j equal to 20. So 20 Arnoldi steps, quite reasonable. And then look at the 20 by 20 submatrix of H. So you're not going to go to the end, to Hn. Going to stop at some point, and you have this nice matrix. It'll be tridiagonal, symmetric tridiagonal, and that's the kind of matrix we know how to find the eigenvalues of. So this is symmetric and tridiagonal, and eigenvalues of that class of matrices are very nice, and they're very meaningful, and they're very close to, in many cases, I won't try to give a theory here, in many cases you get very good approximations. The eigenvalues of this submatrix are sometimes called Ritz values, and they use the eigenvalues of this submatrix, and those are often called Ritz values. And so the first 10 eigenvalues of that 20 by 20 matrix would be, in many, many problems, very reasonable, very fast, very efficient approximations to the low eigenvalues of the big matrix A that you start with. Okay. The reason is that eigenvalue, do you all recognize that eigenvalues, that this is the operation, when I bring Q inverse over here, that I would call these matrices similar. Two matrices are similar if there's a Q that connects them this way. And similar matrices have the same lambdas, the same eigenvalues. So the full matrix Q, if we went all the way to the end, we could find its eigenvalues, but the whole point of all this, of this month, is algorithms that you can stop part way and you still have something really good. Okay, so that's, I think we can't do everything. So I won't try to do more with eigenvalues, but except to mention that. Someday you may want the eigenvalues of a large matrix, and I guess AR pack would be the Arnoldi pack. That would be the package to go to for the Arnoldi iteration, and then to use for the eigenvalues. Okay, so that's a side point, just since linear algebra is half of its linear systems and half of its eigenvalue problems, I didn't think I could miss the chance to do that second half, the eigenvalue problems. Okay, now I'm going to tackle conjugate gradients to get the idea. Okay, so the idea, well, of course, A is symmetric, positive, definite. If it's not, you could try these formulas, but you'd be taking a pretty big chance. If it is, these are just right. Okay, so what's the main point about, here's the rule that decides what xk will be. Xk will be the vector in the Krylov, of course. Xk is in this Krylov space K. So it'll be, we can create xk recursively, and we should need just, if we do it right, should need just one multiplication by A at every step, and then some inner products. Okay, so now, what do we know from this? This vector, so this vector, since it has this, it starts with, it has an xk that's in the kth Krylov subspace, but now it's multiplied by A, so that's up to the K plus first. So this is, and B is in K1, it's in all the Krylov subspaces. So this is in, and therefore RK is in, this is in K plus 1, right? This is in the next space up, because there's a multiplication by A. And therefore, if we choose that to determine it by this rule, we learn that this vector, I mean, we already know from Arnoldi that QK plus 1 is orthogonal to this space. This is the new K plus first vector that's in K plus 1. So this is just where this is to be found. So this vector RK is found in the next Krylov subspace. This one is in the next Krylov subspace. They're both orthogonal to all the previous Krylov subspaces, so one's a multiple of the other. So that will mean that automatically that the R's have the same property that Arnoldi created for the Q's, they're orthogonal. So the residuals are orthogonal. So orthogonal residuals. Orthogonal residuals. Good. I better say, by the way, when we do conjugate gradients, we don't also do Arnoldi. So Arnoldi's finding these Q's. We're leaving him behind for a while because we're going to go directly to the X's and R's here. So I won't know the Q's, but I know a lot about the Q's, so it's natural to write this simple fact that each residual is a multiple of the new Q, and therefore it's orthogonal to all the old ones. And now I want to, this is the other property that determines the new X. So the new X should be, what do I see here? I see a sort of delta X. The change in X, the correction, which is what I want to compute at step K. That's what I have to find. And I could look at the corrections at the old steps, and notice there's an A in the middle. So the corrections to the X's are orthogonal in the A inner product. And that's where the name conjugate comes from. So this is conjugate directions. Why do I say directions and why do I say conjugate? Conjugate gradients, even, I could say. Why do I'll conjugate directions? I maybe shouldn't have erased that, but I'll also say conjugate gradients. Okay. So conjugate, all I mean by conjugate is orthogonal in the natural inner product that goes with the problem, and that's given by A. So the inner product given by the problem is the inner product of X and Y is X transpose AY. And that's a good inner product. And it's the one that comes with the problem, and so natural to look at orthogonality in that sense. And that's what we have. So these are orthogonal in the usual sense because they have an A already built into them. And these are orthogonal in the A inner product. Okay. So I wrote down two requirements on the new X. Well, actually, you might say I wrote down a whole lot of requirements because I'm saying that this should hold for all the previous I's, and this should hold for all the previous I's. And you see indices are getting in here, and I'm asking for your patience. What's the point that I want to make here? It's this short recurrence point, this point that we had over here when H was just tridiagonal. So we only needed, at the new step, the only things we had to find were say at the second step, we just had to find that H and that H because this one was the same as that. And then the next one, maybe didn't say that right. I guess when let me start again. At the first step, I need to find two numbers. Now, because H is symmetric, that's already the same as that. So at the next step, I need these two numbers. And then that number is already that. So two numbers at every step. And big zeros up here. That's the key point when A is symmetric. So the same will be true over here. We have two numbers, and they're called alpha and beta. So they're little different numbers because we're working with the x's now and not with the q's. So you don't see any q's written down for conjugate gradients. Okay. All right, let me just look at the cycle of 5 steps. You start with, so I have to give it a start. So I start with D0 as B and X0 as 0. And I guess R0, which of course is B minus A X0, if that's 0, it's also B. So those are the start. So I'm ready to take a step. I know the ones with subscript 0, and I'm ready for the next step. I know the ones with subscript K minus 1, and I'm ready for this step, this cycle, K. All right. So here's a number. So I'm coming into the cycle. Well, let me say maybe how I should say it. I'm coming into that cycle with a new D. Now, what is a D? It's a search direction. It's the way I'm going to go. It's the direction in which this delta x is going to go. This delta x is going to be, probably I'll see it here. Yeah, there's delta x is a multiple of D. Right? If I put this on this side, that's delta x. The change in x is a multiple of D. So D is the direction in n-dimensional space that I'm looking for the correction. And alpha is the number, is how far I go along D for the best, for the right delta x. So alpha will be determined by, probably by that. Probably by that, yeah. Yeah, it involves it involves an inner product. I'm picking off a component. Okay, so the first step is to find a number. The next step is to take that update. Delta x is the right multiple of the search direction that I'm coming in with. Then correcting R is easy. I'll come back to that. If I know the change in x, I know the change in R right away. So that's given me, I'm now updated. But now I have to look ahead. What direction am I going to travel next? So the next steps are to find a number beta, and then the search direction, which isn't R, it's R again with just a one correction there. So it's a beautiful set of formulas, beautiful. And I could write, because I know X's and R's, I could write these formulas in, there are different expressions for the same alpha and beta, but this is a very satisfactory one. Okay, have a look at that cycle just to see how much work is involved. How much work is involved in that cycle? Okay, well, there's a multiplication by A. No surprise. It's that multiplication by A that takes us to the next Krylov space, takes us to the next update. So I see a multiplication by A, and also here, but it's the same multiplication. So I see one multiplication by A. So easy to list. So each cycle, there's one multiplication A times the search direction. And because A is a sparse matrix, that's the cost there is the number of non-zeros in the matrix. Okay? Then what else is? What other computations do we have to do? I see an inner product there, and I'm going to use it again. I guess, and here it is at the next step. So I guess per cycle, I have to do one inner product of R with itself, and I have to do one of these inner products. So I see two inner products. And of course, these are vectors of length n, so that's 2n multiplications, 2n additions. Okay, this was a multiple of n, depending how sparse A is. This is 2n adds and 2n multiplies for these two inner products. Okay. Okay. Yeah, I guess you could say take them there. Right. Okay. And then what else do we have to do? Oh, we have these updates. So I have to multiply a vector by that scalar and add. So I have, and again here, I multiply that vector by that scalar and subtract. Oh, and do I have to do it again here? Have I got 3? Somehow I thought I might only have 2. Yeah, 2 or, let me say 2 or 3 vector updates. Vector updates. People are much better than I am at spotting the right way to organize those calculations. But that's really a very small price to pay per cycle. And so if it converges quickly, as it normally does, this is going to be a good algorithm. Maybe having introduced the question of how quickly does it converge, I should maybe say something about that. So what's the error after k steps? How is it related to the error at the start? So I have to first say, what do I mean by this measure of error? And then I have to say, I hope I see a factor less than 1 to the kth power. Yeah, so I'm hoping some factor to the kth power will be there. And I'm sure hope it's less than 1. Let me say what it is. I think, so this is maybe not the very best estimate, but it shows the main point, is the square root of lambda max minus the square root of lambda min divided by the square root of that plus the square root of that. And maybe there's a factor 2 somewhere here. So this is one estimate for the convergence factor. And you see what it depends on? I could divide everything by lambda min there, so that I could write that as the square root of the condition number, because I'll divide by that, minus 1, divided by the square root of the condition number plus 1 to the kth power. So the condition number has a part in this error estimate. And I won't derive that. Even in the notes, I won't. Yeah. And it's, other people work out other estimates for the error. It's an interesting problem. And I do have to say that this norm is the natural inner product. EK squared is the inner product of EK with itself, but again with A in the middle. I suppose that a little part of the message here and on that middle board is that it's just natural to see the matrix A playing a part in the, it just comes in naturally conjugate gradients brings it in naturally. These formulas are just created so that this will work. Okay. So I suppose I'm thinking there's one word I haven't really justified, and that's the word gradient. Why do we call it conjugate gradient? Here I erased a conjugate directions I was quite happy with. The directions are the D's. Because this is the direction in which we move from X. So conjugate directions would be just fine, and those words come into this part of numerical mathematics. But where do gradients come in? Okay, so let me say gradient of what? Well, what is, so first of all, the gradient of what is, in these linear problems, where AX equal B, those come from the gradients of the energy. So can I say E of X for the energy as 1/2 X transpose AX minus B transpose X? You might say, where did that come from? Normally we've been talking about linear systems. Everything's been in terms of AX equal B. And now suddenly I'm changing to a different part of mathematics. I'm looking at minimizing, so optimization, the part that's coming in April, is minimizing energies, minimizing functions. And what's the link? Well, if I minimize that, the gradient of this is, how shall I write? Grad E, the gradient of E, the list of the derivatives. This is the derivatives of E with respect to the xi. And if we work that out, well, why not pretend it's scalar for the moment? So these are just numbers. Then this ordinary derivative of 1/2 AX squared is AX. And the derivative of BX is B. And that rule continues into the vector case. So what have we got here? We've introduced the natural energy. So this is the natural energy for the problem. And the reason it's natural is when we minimize it, set the derivatives to 0, we get the equation AX equal B. So that would be 0 at a minimum. This would equal 0 at the min. So what I'm doing right now is pretty serious. On the other hand, I'll repeat it again in April when we do minimizations. But this quadratic energy has a linear gradient, and its minimum is exactly AX equal B. The minimum point is AX equal B. In other words, solving the linear equation and minimizing the energy are one and the same. One and the same. And I'm allowed to use the word min because A is positive definite. So the positive definiteness of A is what means that this is really a minimum and not a maximum or a saddle point. Okay, so I wanted just to think about how do you minimize a function? I guess any sensible person, given a function and looking for the minimum, would figure out the gradient and move that way. Move, well, not up the gradient, move down the gradient. So I imagine this minimization problem. I imagine here I'm in X. This is the X, X1, X2, the X's. here's the E of x is something like that. Maybe its minimum is there. This is a graph of E of x. And I'm trying to find that point. And I make a first guess somewhere there. Somewhere on that surface. Maybe just so to help your eye, this is like a bowl. And maybe there's a point. So that's on the surface of the bowl. That's x0, let's say. I'm trying to get to the bottom of the bowl. And as I said, any sensible person would figure out, well, what's the steepest way down? The steepest way down is the direction of the gradient. So I could call this gradient G if I wanted. And then I would go in the direction of minus G because I want to go down and not up. I mean, we're climbing, I shouldn't say climbing, we're descending a mountain and trying to get to or descending a valley, sorry. We're descending into a valley and trying to get to the bottom. And I'm assuming that this valley is this nice shape given by just a second-degree polynomial. Of course, when we get to optimization, this will be the simplest problem, but not the only one. Here, it's our problem. Now, of course, so what happens if I move in the direction of the direction water would flow? If I tip a flask of water on the ground, it's going to flow in the steepest direction. And that would be the natural direction to go. But it's not the best direction. Maybe the first step is. But I'm talking now about conjugate gradient seen as a minimization problem, because that's where the word gradient is justified. This is the gradient, and of course, this is just minus the residual. So this is the direction of the residual. So that's the question. Should I just go in the direction of the residual all the time? At every step? And this is what the method of steepest descent will do. So let me make the contrast. Steepest descent is the first thing you would think of. Direction is R. That's the gradient direction, or the negative gradient direction. Follow R until in that direction you've hit bottom. So you'll go down this, right, do you see what happens? You'll be going down one side and you'll hit bottom, and then you'll come up again on a plane that's cutting through the surface. But you're not going to hit that first shot. When you start here, see, water would, the actual steepest direction, the gradient direction, changes as the water flows down to the bottom. But here we've chosen a fixed direction, we're following it as long as we're going down, but then it'll start up again. So we stop there. And find the gradient again there. Follow that down till it goes up again. Follow that down until it goes up again. And the trouble is, convergence isn't great. The trouble is that we end up, even if we're in 100-dimensional space, we end up sort of just our repeated gradients are not really in good new directions. We find ourselves doing a lot of work to make a little progress. And so the reason is that these R's don't have the property that you're always looking for in computation, orthogonality. Somehow orthogonality tells you that you're really getting something new if it's orthogonal to all the old ones. Okay. Now, so the direction R is not great. The better one is to have some orthogonality. Take a direction D that, well, here's the point. This is the right direction. This is the direction conjugate gradients choose. This is where, so it's a gradient, but then it removes the component in the direction we just took. That's what that beta will be. That's what, when we compute that beta, and I'm a little surprised that it isn't a minus sign. No, it's okay. Yeah, it turns out that way. Let me just be sure that I wrote this formula down right. At least wrote it down as I have it here. Yep. Again, I'm not checking the formulas, but just describing the ideas. So the idea is that this formula gives us a new direction, which has this property too that we're after, that the direction, it's not actually orthogonal, it's orthogonal to the previous directions. Okay, I'm going to draw one picture of what, whoops, not on that, of these directions. And then that's my best I can do with conjugate gradients. I want to try to draw that this search for the bottom of the valley. So I'm going to draw that search by drawing the level sets of the function. I'm going to somehow the contours of my function are, since my function here is quadratic, all the contours, the level sets will be ellipses. They'll all be sort of like similar ellipses, and there's the one I want. That's the bottom of the valley. So this is the contour where energy 3, this is the contour energy 2, this is the contour energy 1, and there's the point where the energy is a minimum. Well, it might be negative, doesn't, whatever, but it's the smallest. Okay. So can I compare steepest descent with conjugate gradients? Let me draw one more contour just so I have enough to make this point. Okay. So steepest descent starts somewhere. Okay. Starts there, let's say. Suppose that's my starting point. Steepest descent goes, if I draw it right, it'll go perpendicular, right? It goes perpendicular to the level contour. You carry along until, as long as the contours are going down, and then if I continue here, I'm climbing back up the valley. So I'll stop here. Let's suppose that happened to be tangent right there. Okay. Now, that was the first step of steepest descent. Now I'm at this point. I look at this contour, and, well, if I've drawn it reasonably well, I'm following maybe perpendicular. And now again, I'm perpendicular. Steepest descent says go perpendicular to the contour until you've got to the bottom there. Then down. Then up. Then do you see this frustrating crawl across the valley? It wouldn't happen if these contours were circles. If these contours, if A was the identity matrix, these would be perfect circles, and you'd go to the center right away. Well, that only says that AX equal B is easy to solve when A is the identity matrix. So this is steepest descent. And its rate of convergence is slow. Because its rate of, the longer and thinner the valley, the worse it is here. Okay. What about conjugate gradients? Well, I'm just going to draw a magic I'm going to make it look like magic. I'm going to start the same place. The first step, because I'm starting with 0, the best thing I can do is follow the gradients to there. And now, so that was the first step. And now what? Well, the next direction. So these are the search directions. That's the search direction D1, D2, D3, D4. Here's D1, and what does D2 look like? May I cheat and go straight to the center? That's a little bit of a cheat. I'll go near the center. The next direction is much more like that, and then it goes to the bottom, which would be somewhere like there inside that level set. And then the next direction would probably be very close. So this is not 90 degrees unless you're in the A inner product. So this is a 90-degree angle in the A inner product. And what does the A inner product do? In the A inner product, in which level sets are circles or spheres or whatever in whatever dimension we want. Well, I'm not going to I don't want to be held to everything here. If you see this picture, then we've not only made headway with the conjugate gradient method, which is a big deal for solving linear systems, but also we've made headway with the conjugate gradient method for minimizing functions. And if the function wasn't quadratic and our equations weren't linear, the conjugate gradient idea would still be available. Nonlinear conjugate gradients would somehow follow this same idea of A orthogonal search directions. So these are not the gradients, they're the search directions, really. Okay. That's sort of my speech about the conjugate gradient method. Without having checked all the formulas in the cycle, we know how much work is involved, we know what we get, and we see a bit of the geometry. Okay, and we see it as a linear system solver and also as a energy minimizer. And those are both important ways to think of conjugate gradients. Okay, I'll just take a few final minutes to say a word about what if our problem is not symmetric positive definite? What if we have an unsymmetric problem or a symmetric but not positive definite problem? Well, in that case, these denominators could be 0. They could, I mean, if we don't know that A is positive definite, that could be a 0. It could be anything, and that method is broken. So I want to suggest a safer but more expensive method now so this will be minres minimum residual. So the idea is choose xk to minimize the norm of rk. That's the residual. So minimize the norm of b minus ax. K. Okay, so that's my choice of xk. And the question is, how quickly can I do it? So this is minres. Okay. And there are other related methods. So there's a whole family of methods. What do I want to say about minres? Let me just find minres. Well, yeah. I guess for this I will start with Arnoldi. So for this different algorithm, which comes up with a different xk, I'm going to, and of course the xk is going to be in the Krylov space kk, and I'm going to use this good basis. This gives me the basis of the great basis of Q's. So I turn my problem. I convert the problem. I convert this minimization. I look for x. I look for x as a combination of the Q's. Right? Is that how you see x equal qy? So instead of looking for the vector x, I'm looking for the vector y, which tells me what combination of these columns, the q's, x is. In other words, I'm working in the q system, the q basis. So I'm working with y. So I would, naturally, write this as the minimum of b minus a q y k. Same problem. Same problem. I'm just deciding, okay, I'm going to find this x as a combination of the q's because those q's are orthogonal, and that will make this calculation a lot nicer. Okay, what's going to happen here? You know that I'm going to use the property of the q's, that AQ is QH. That was the key point that Arnoldi achieved. And the net result is going to be, of course, I have to do this at level K, so I'm chopping it off. And I have to patiently, and the notes do that, patiently see, okay, what's happening when we chop off these matrices. We have to watch where the non-zeros appear. In the end, I get to a minimization problem for y. So we get to a minimum problem for the matrix H, for the matrix H that leads me to the y. Okay, the y that I'm after. So it's a minimum problem for a piece, sorry, I should really say H, K, some piece of H, like this piece. In fact, exactly that piece. So if I ask, all right, suppose I have a least squares problem. This is least squares because my norm is just the square. The norm squared. I'm just working with L2 norm. And here's my matrix. Then it's 3 by 2. So I'm looking at least squares problems in that matrices of that type, and they're easy to solve. The notes will give the algorithm that solves the least squares problem. I guess what I'm interested in here is just, is it expensive or not? Well, the least squares problem will not be expensive. It's only got one extra row compared to the number of columns. That's not bad. What's expensive is the fact that our H is not tridiagonal anymore. These are not zeros anymore. So the next problem, I have to compute all these H's. So the hard work is back in Arnoldi. So it's Arnoldi leading to minres, and the work is, we have serious work already in Arnoldi. We don't have short recurrences. We've got all these H's. Okay, enough, because these RPAC would be a good code to call to do minrisk. Okay, that's my shot at the key Krylov algorithms of numerical linear algebra. And you see that they're more subtle than Jacobi. Jacobi and Gauss-Seidel were just straight, simple iterations. These have recurrence that produces orthogonality, and that's you pay very little and you get so much. Okay, so that's Krylov methods, and that section of notes is up on the web. And of course, at some point, numerical comparisons of how fast is conjugate gradient, and is it faster than direct elimination? You know, because that's a big choice you have to make. Suppose you do have a symmetric positive definite matrix. Do you do Gauss elimination with reordering, minimum degree, or do you make the completely different choice of iterative methods like conjugate gradients? And that's a decision you have to make when you're faced with a large matrix problem, and only experiments can compare two such widely different directions to take. So I like to end up by emphasizing how that there's still a big question. Do this or do minimum degree, and only some experiments will show which is the better. Okay, so that's good for today, and next time will be direct solution using the FFT. Good, thanks.